Hello guys, thank you so much for having me here today. So I've called this Navigating LLM Deployment Tips, Tricks and Techniques 2.0. I gave this talk in London about 6 months ago, and I was kind of hoping I could just reuse the same presentation because, you know, a bit lazy like that, but unfortunately the space evolved so quickly I had to completely rewrite it. So it's a completely different presentation more or less to what I did in London. I could also rename it How to Deploy LLMs If You Don't Work at Meta, OpenAI, Google, Mistral, or Anthropic. If you do work at one of these places, you can still stay, but it might be less interesting to you. I'm specifically interested in how you deploy LLMs if you're not serving it as a business, and instead you're serving it so you can build applications on top of it. And you end up deploying it in fairly different ways if you work at a normal company versus one of these guys. Out of interest, hands up if you don't work at one of these guys. Okay, cool. So there's some relevant people here. That's good. So hopefully you're going to get 3 things out of this session. Firstly, you're going to learn when self-hosting is right for you, because you're going to find out it can be a bit of a pain, and it's something you should only do if you kind of really need to. Understanding the differences between your deployments and the deployments of AI labs. And then also, I'm going to give some best practices, tips, tricks, techniques, a non-exhaustive list for how to deploy AI in corporate and enterprise environments. So, first, this is me. There's my QR code to connect on LinkedIn. I'll also show it again at the end. Essentially, we build infrastructure for serving LLMs. So, firstly, when should you self-host? To explain what that is, I'll just clarify what I mean by self-hosting. I distinguish self-hosting compared to interacting with LLMs through an API provider. So this is how you interact with LLMs through an API provider. They do all of the serving and hosting for you. It's deployed on their GPUs, not your GPUs. They manage all of that infrastructure, and what they expose is just an API that you can interact with. That's what an API hosted model is. And all of those companies I mentioned at the beginning host these models for you. Versus being self-hosted. So when you self-host, you're in control of the GPUs. You take a model from Hugging Face or wherever you're taking that model from, and you deploy it and you serve it to your end users. This is kind of the broad difference. It's essentially a matter of who owns the GPUs and who's responsible for that serving infrastructure. So why would you ever want to self-host? Because when people manage things for you, your life's a little bit easier. But there are 3 main reasons why you'd want to self-host. The first one is you have decreased costs. Well, I should clarify that. You have decreased costs when you're starting to scale. At the very, very early stages of POCing and trying things out, you don't have decreased costs. It's actually much, much cheaper to use an API provider where you pay per token and the per token price is very low. But once you get to any kind of scale where you can fully utilize a GPU, or close to it, it actually becomes much more cost efficient. The second reason why you'd want to self-host is improved performance. So this might sound counterintuitive because on all the leading benchmarks, the GPT models and the Claude models are best in class for those benchmarks. However, if you know your domain and you know your particular use case, you can get much better performance when self-hosting. This is especially true, and I'm going to talk about this a bit more later. This is especially true for embedding models, search models, re-ranker models. The state of the art for most of them is actually in open source, not in LLMs. So if you want the best of the best breed models, you'll have a combination of self-hosting for some models and using API providers for others. So you can get much better performance by self-hosting. And some privacy and security. I'm from Europe, and we really care about this, but we also work with regulated industries here in the US, where you have various reasons why you might want to deploy it within your own environment. Maybe you have a multi-cloud environment, or maybe you're still on-prem. And this kind of sits with the data that A16Z collected, that there's broadly 3 reasons why people self-host: control, customizability, and cost. So it is something that a lot of people are thinking about. So how do I know if I fall into one of those buckets? Well, broadly, if I care about decreased cost, that's relevant to me if I'm deploying at scale. Or it's relevant to me if I'm able to use a smaller specialized model for my task rather than a very, very big domain, like very big general model like GPT-4. If I care about performance, I will get improved performance if I'm running embedding or re-ranking workloads, or from operating in a specialized domain that might benefit from some fine-tuning, or I have very clearly defined task requirements. I can often do better if I'm self-hosting rather than using these very generic models. And finally, on the privacy and security things, if you might have legal restrictions, you'll obviously then have to self-host. Potentially, you might have region-specific deployment requirements. So we work with a couple clients who, because of the various AWS regions and Azure regions, they have to self-host to make sure they're maintaining that sovereignty in their deployments. And then finally, if you have multi-cloud or hybrid infrastructure, that's normally a good sign that you need to self-host. A lot of people fall into those buckets, which is why the vast majority of enterprises are looking into building up some kind of self-hosting infrastructure. Not necessarily for all of their use cases, but it's good to have as a sovereignty play. I'm going to make a quick detour, and I also felt very cringy making a slide which had a screenshot of my own LinkedIn post on it, but I thought my LinkedIn post was quite good in this case. Quick public service announcement that I mentioned embedding models, and I mentioned that the state of the art for embedding models is actually in the open source realm, or they're very, very, very good. There's another reason why you should almost always self-host your embedding models. And the reason why is because you use your embedding models to create your vector database, and you've indexed vast amounts of data. If that embedding model that you're using through an API provider ever goes down or ever is depreciated, you have to re-index your whole vector database. That is a massive pain. You shouldn't do that. They're very, very, very cheap to host as well. Always self-host your embedding models. That's a quick announcement. Back to our regular scheduled programming. So when should I self-host versus when should I not? I've been a little bit cheeky here. Good reasons to self-host. You're building for scale. You're deploying in your own environment. You're using embedding models or re-ranker models. You have domain-specific use cases, or my favorite one, you kind of have trust issues. Someone hurt you in the past, and you want to be able to control your own infrastructure. That's also a valid reason. Bad reasons to self-host is because A, you thought it was going to be easy. It's not easier necessarily than using API providers. Or someone told you it was cool. It is kind of cool, but that's not a good reason. So that's how you should evaluate whether self-hosting is right for you. If you fall into one of these on the left, you should self-host. If not, you shouldn't. So understanding the difference between your deployments and the deployments in AI labs. So if I'm for example, an OpenAI, and I'm serving these language models, I'm not just serving one use case. I'm serving literally millions and millions and millions of different use cases. And that means I end up building my serving stack very, very differently. Let's say I'm hosting with an enterprise or corporate environment. Maybe I'm serving, 20 use cases, like in a more mature enterprise. Maybe I'm serving now like just a couple. And because I have that difference, I'm able to make different design decisions when it comes to my infrastructure. So here are a couple reasons why your self-hosting regime will be very different to the OpenAI self-hosting regime. First one is they have lots and lots and lots of H100s and lots of cache. My guess is the majority of you guys don't have lots of H100s and are probably renting them via AWS. They're more likely to be compute bound because they're using the GPUs like H100s rather than things like A10s. They have very little information about your end workload. So they are just kind of going on we're just trying to stream tokens out for arbitrary workloads. You have a lot more information about your workload. And they're optimizing for one or two models, which means they can do things that just don't scale for regular people self-hosting. If I'm deploying just GPT-4, then I'm able to make very, very, very specific optimizations that only work for that model, which wouldn't work anywhere else. So if you're not self-hosting, you're likely using cheaper, smaller GPUs. You're probably using also a range of GPUs, so not just one type. Maybe you're using a couple different types. You're more likely to be memory bound than compute bound. You have lots of information about your workload. So this is something that is very exciting, that for most enterprises, the workloads actually look kind of similar, which is normally some kind of like long form RAG or maybe extraction task, and you can make decisions based on that. And you'll have to deal with dozens of model types, which is a luxury. You don't have the luxury of those AI labs. So here are some differences between the serving that you'll do and the serving that your AI labs will have to do. So, best practices. There are literally an infinite number of best practices that I could give, but I've tried to boil them down to, I think it's now 6, because I think I added one this morning. 6 non-exhaustive tips for self-hosting LLMs. This isn't a complete guide to self-hosting, but hopefully there are some useful things that we've learned over the last couple of years that might be useful to you. The first one is know your deployment boundaries and work backwards. Quantized models are your friends. Getting batching right really, really matters. Optimize for your workload. So that goes back to what I said earlier about you can do optimizations that they just can't. Be sensible about the models you use. And then finally, consolidate infrastructure within your org. These are the top tips that I'm going to talk through now for the rest of the session. So let's start with deployment boundaries. Assuming you don't have unlimited compute, and to be honest, even the AI labs don't have unlimited compute. It's a really, really scarce resource at the moment. You need to be very, very aware of what your deployment requirements are, and then work backwards from what you know about them. So if you know you only have a certain available hardware, maybe you're, for example, just CPU bound and you're deploying completely on-prem and you don't have GPUs, then you probably shouldn't be looking into deploying a Llama 4 or 5 billion. So knowing that kind of boundary is important from the get-go. You should have an idea of your target latency as well, and you should have an idea of your expected load. If you have all of these together, and you can construct some kind of sentence of, I would like to deploy on an instance cheaper than X, which will serve Y concurrent users in an average latency of, I don't know, less than Z. If you can form that kind of sentence, it makes everything else that you'll have to do much easier, and you won't kind of have that bottleneck of being like, oh, I built this great application, I just have no idea how to deploy it. I can use that kind of information to then work backwards and figure out what kind of models I should be looking at, and how much effort I should be putting into things like prompting and really refining my search techniques rather than upgrading to bigger models. Which leads me on to my second tip, which is you should pretty much always be using quantized models for a couple different reasons. The first reason I'm going to say is that you should always use quantized models more or less is because the accuracy is pretty much always better than a model of that same memory requirement that you've quantized it down to. So you retain a lot of that accuracy. And the second reason that you should pretty much always quantize is because actually the accuracy loss isn't that different from the original model. And I'll reference 2 pieces of research that show this. So there was this paper that came out, I think it was last year, in 2023, I believe, by Tim Detmers, amongst others, who's a bit of a legend in the field. And it's called The Case for 4-Bit Precision. And what he showed in this paper, I can show you the kind of highlight figure, is that for a fixed model bit size, the accuracy of the model is far, far higher if you're using a quantized model. So given that we know when we have a model with more and more parameters, as I scale up the parameters, the accuracy of the model goes up and up and up. But what's interesting is if I take one of those large models and quantize it down to a natively smaller size, it retains a lot of that accuracy that we had in the beginning, which is very, very good. So I'm pretty much always going to have better performance using a quantized 70 billion parameter model than I will of a model of a native size. This goes on to some great research that Neural Magic did on this. So they showed that, firstly, if I quantize models, so here they have the accuracy recovery. So this is when they quantize, take original bit precision models and then quantize them. It pretty much retains all of the accuracy from the original model, which is great. So, I mean, you get to like 99% accuracy maintenance, which is awesome. And you can see that even though there are slight dips in the performance, so for example, if I look at this 405 here, with one of the quantized variants, it's a slight dip in the original, it's like a couple of basis points. It's still far, far, far higher than the 70 billion parameter or the 8 billion parameter model. So it retains much of that accuracy that you were looking for. So if you have, if you know your deployment boundaries and you don't have like unlimited amounts of compute to call from, using that quantized model, using the best model that will fit within that is a great piece of advice. So if I know that this is the piece of infrastructure I'm working with, this is the GPU I'm working with, I can then say, okay, which is the biggest model that when quantized down to 4-bit is going to perform the best. So in this case, this is a couple months old, Mixtral is not really a thing anymore, but you get the idea that I would rather use the Mixtral 4-bit, which is in 22 gig, than the Llama 13B, because it's retained a lot of that performance. And I put at the bottom places that you can find quantized models. We retain an open source bank of quantized models that you can check out. The bloke also used to be a great source of this as well, although he's not doing it as much recently. The third thing I'm going to talk about is batching strategies. This is something that's very, very important to get right. And the reason it's very important to get right is because it's a very easy way to waste GPU resources. So when you're first deploying, you're probably not using any batching, which means you end up with GPU utilization coming like this. It's not great. We then see people going straight to dynamic batching. So what this means is I have a set batch size. So let's say my batch size is 16. I will wait until 16 requests have come in to process, or I'll wait a fixed amount of time. And you end up with this kind of spiky GPU utilization, which is still not great either. What's far, far better if you're deploying generative models, so very big piece of advice, is to use something like continuous batching, where you can get consistently high GPU utilization. It's a state-of-the-art technique designed for batching of generative models, and it allows requests to interrupt long in-flight requests. And this batching kind of happens at the token level rather than happening at the request level. So I could, for example, have my model generate the 65th token of one response and then the 5th token of another response. And I end up with a utilization that is far, far, far more even. This is just one of the examples of like inference optimizations that you can do that make really big difference. So here I think I've gone from a 10% utilization to near enough 80. So really significant improvements. And if you're in a regime where you don't have much compute environment or compute resource, this is a very, very valuable thing to do. Okay, I'm going to talk about workload optimizations. Now this is something I didn't have when I did the London talk. And it's something that we've been researching a lot actively and we think is really promising. So you know something that the AI labs don't know, which is what your workload looks like. And what that means is you can make a lot of decisions based on what your workload looks like that it would just never, ever make sense for them to make. So I'm going to give you a couple examples of techniques that you can use that make sense if you know what your workload looks like, that don't make sense if you're serving like big multi-tenant environments into multiple user groups. So one of them is prefix caching. This is probably one of the things I'm most excited by that happened this year. So one of the most common use cases that we see from our clients is situations where they have really, really long prompts. And often these prompts are shared between requests. So maybe what I have is I have a very long context RAG on like a set document that maybe I just pass through the whole document and I'm asking questions of it. Or maybe I have a situation where I have a very, very long set of user instructions to the LLM. So these are instances where I have very, very long prompts. And traditionally, what I would have to do is I'd have to reprocess that prompt every single request, which is super inefficient. But what we can do, if you know what your workload looks like and you know that you're in a regime where you have a lot of shared prompts or very, very long shared prompts, you can use something called prefix caching, which is essentially when you pre-compute the KV cache of text and you reuse that when the context is reused when you do your next generation. So my LLM doesn't need to reprocess that long prompt every single time. They can process just the difference between them. So if I have a very, very long shared prompt and then slightly different things each time, it can just process that difference and then return. So on the right, I have some results that are fresh off the press. So my team sent me them yesterday. What we have here is our server with the prefix caching turned on and turned off. So in the green lines, we have it with turned off. The light green line is with 2 GPUs and the dark green line is with 1 GPU. And with the blue line, we have it with the prefix caching turned on. And what you can see is we have very, very significant throughput improvement. So it's throughput on the Y and then batch size on the X, about 7x higher throughput, which is very, very significant. It means that you can process many, many more requests, or you can process those requests much, much cheaper. This has like no impact if you didn't know that you had a long shared prompt. It doesn't really have an impact if I'm serving multiple dozens of users at any one time. This only really works if I know what my use case looks like. Another example of caching that we're really excited by, so we call this internally SSD, which is a form of speculative decoding, but you can also think of it like caching, which only makes sense if you know what your workload looks like. So this is a use case where if your model might predict similar tokens between tasks. So let's say I'm doing a task where I have phrases that are very, very frequently repeated. What I can do is I can essentially cache those very frequently repeated phrases, and instead of computing the whole phrase every single time, token by token, I can just pull a cache hit and inference on that. So we did benchmarking on this last week, and for a workload, it was a JSON extractive workload. We got about a 2.5 latency decrease on this, which is pretty significant. Again, would have literally no impact if I'm using the OpenAI API, because there's no way they could cache your responses and 75 million other people's responses. So it only really makes sense if you're deploying in your own environment. Cool. So I have 2 more that I'm going to go through. This one is model selection. I think everyone knows this by now, but the only real reason I put it up is because last time people really liked the the image. This is something that I still see people getting wrong, which is they get their large language models, which are the most difficult things to deploy and the most expensive things to deploy, to do pretty much all of the workload. And that's not a good idea. And the reason it's not a good idea is because you then have more of this difficult, expensive thing to manage. There are a lot of parts to an enterprise RAG pipeline. In fact, the most important part of your enterprise RAG pipeline is actually not the LLM at all. The most important part is your embedding and retrieval part, by far. And they don't need GPT-4 level reasoning, obviously. And if you have really good search and retrieval pipelines, you can actually use much, much, much smaller models to get the same kind of results. So we've seen clients move from GPT-4 type setups to move to things as small as the Llama 2 billion models if they get their retrieval part right, which means you can run the whole application very, very cheaply. I would advise people to check out the Gemma and the small Llama models for this. We think they're very, very good on extractive workloads as well, especially if you're using a JSON structured format like outlines or LMFE. So pick your application design carefully and only use big models when you really need to use big models. Finally, I'm going to talk about infrastructure consolidation. In traditional ML, most teams actually work in silos still, unfortunately, which is they deploy their own model and they're responsible for deploying their own model. In Gen AI, it does not make sense to do that. And that's why these API providers are making an absolute killing, because it does make sense to deploy once, manage centrally, and then provide it as a shared resource within the organization. And if you do this, it enables your end developers to focus on building this application level rather than building infrastructure. So when I speak to my clients, sometimes we talk about like building an internal version of the OpenAI API. That's kind of the experience you want to be able to provide to your developers, because otherwise they'll have to learn what prefix caching is every single time they want to deploy a model, which is just not an efficient use of time. So I think this kind of centralization is a really exciting opportunity for ML ops teams to take that kind of ownership within the org. This still means, you can understand the kind of workloads you work with and optimize for example, long context RAG situations. That's still something that you can do. And so you can actually end up making a cheaper and better version of something like the OpenAI API. So serving is hard. Don't do it twice or even three. Or we've seen clients who do it over and over again. So you'll have a team deploying with Olama, another team deploying with LLM, and trying to do it. Much better to have a central team manage that. And GPUs are very expensive. Don't waste them. So I can talk about what this would actually look like in practice. This central consolidation of infrastructure, you can kind of think of it as having like an internal Bedrock or an internal OpenAI API or something like that. And individual ML teams can work from these APIs and then build applications on top of them using techniques like LoRa, so that's a form of fine-tuning, or use things like RAG, where they're plugging into it in the same way they use the OpenAI API. We have a quick case study. So a client of ours did this. So they started off with a bunch of different models. Each app was essentially attached to its own model and attached to its own GPU setup. This is obviously not ideal because I'm deploying, for example, at the time it was a Mixtral. We were deploying that multiple times over and over again and wasting GPU resources. Instead, what we did is we just kind of pulled it into one and deployed that Mixtral on a centrally hosted infrastructure, which meant we could use much, much less GPU resource than we were using otherwise. So something that I like the pattern of is giving your team, so if you're doing this central deployment and central hosting, is give your team access to a couple of different models of different sizes, give them optionality. So don't say something like, you can only use this particular model because they want to be able to try things. But deploying like a large, medium, and small model that you guys have checked out and that you're happy with is a really good place to start with a bunch of, maybe those auxiliary models, so table parsers, embedding models, re-ranker models, et cetera, et cetera. If you do that, you give your team optionality and you still maintain the benefit of being able to consolidate that infrastructure and make those optimizations. So there's my 6 non-exhaustive tips for self-hosting LLMs. Know your deployment boundaries and work backwards. If you do know this, everything else becomes much easier. Quantized models are your friends. They might seem scary because they affect the model, but they're actually, on the whole, much better. Getting batching right really matters for your GPU utilization. Optimize for your particular workload. You have a superpower that the API providers do not, which is you know what your workload will look like. Be sensible about the models you use, and then finally consolidate infrastructure within your organization. So today we've gone through why you should self-host, and there's a bunch of infrastructural reasons why self-hosting is a great idea. If you're deploying at scale, if you want to use embedding models, re-ranker models, if you, for example, are using domain-specific models, all very good reasons to self-host. Your needs in deploying will be different to the needs of AI labs and mass AI API providers because you're using different types of hardware and your workloads are different. And I've also given 6 tips, best practices that we've learned over the last couple of years for deploying LLMs in this kind of environment. So thank you very much. And any questions?
As usual, there's lots of great tips there. So if you have any questions, raise your hand. We'll give the mic to you. If not, let me start your question. For those tips that you gave, if I have a bursty workload, are any of those tips more relevant than others?
That's a great question. So if you have a bursty workload, that's it's kind of rough, right? Because there's always going to be some kind of cold start problem when you're deploying these. So for bursty workloads, they're slightly less well suited for self-hosting unless you're deploying smaller models. So if you're deploying smaller models, the scaling up and scaling down is much, much easier. But if you're deploying bigger models, consider whether you do need to actually self-host or whether you can use other providers. We have, within our infrastructure, have obviously built Kubernetes resources that can do that scaling up and scaling down. But if you have bursty workloads with very, very low latency requirements, that is just challenging. What you could do, and what we have seen people do, is if they have a bursty workload, migrating to smaller and cheaper models during the periods of like high burst, and then going back to the higher performance models when things are a bit more chill. So you could imagine a regime where you had a 70 billion parameter model servicing most of the requests, and then let's say you get to periods of very, very high load. While you're waiting to scale up, you move to something like an 8 billion parameter model or something slightly smaller. You take a small accuracy hit and then go from there. So that's something that we've seen work as well.
Any other questions? So there's hands there.
Hi, thank you. Great talk. One question would be, how would you architect kind of a central compute infra if each downstream application requires different fine-tuning, where you can't really have an internal OpenAI API-like serving infrastructure?
That's an awesome question. Let's go back to him. So that's very difficult if you want to do something like full fine-tuning, which we've been used to over the last couple of years, which essentially you fine-tune the whole model. Because what that means is every single time you fine-tune the model, you have to deploy a separate instance of it. Fortunately, over the last, I guess, like 2 years, there's been advancements in PEFT methods, which is essentially a way that you can fine-tune, but you don't have to fine-tune the whole model. You can just fine-tune a small subsection of it. So let's say I have a situation where I'm centrally hosting, and I have 10 different teams, and every single team has done a fine-tuned version of a llama model, for example. What I used to have to do is go in and deploy each of those on like their own GPUs or shared GPUs. What I can do now instead is just deploy a llama model, like a centrally hosted llama models, and then deploy on the same GPU still, in my same server, all of these different LoRa fine-tuned versions. So these small adapters that we add to all of the models. And on inference time, we can hot swap them in and out. So it's like you're calling separate models, but actually it's one base models and these different adapters. And that's really, really exciting because it means we can deploy hundreds, if not thousands, of fine-tuned domain-specific models with the exact same infrastructure and resource that we needed to deploy one. So that's the way I would go about it. PEFT methods, I mean, we prefer LoRa's as a method, but there are other available on the market.
Yeah, one quick question. So you're speaking a lot about the models themselves, which is awesome. But in your diagrams, when you're referring to GPUs and all the work that you did, should we assume most of this is based on HB100 Blackwell, NVIDIA, or did you actually go across Gaudi and Instinct from AMD and so on and so forth? Just curious, because we're looking to build something, and support for all models is not ubiquitous right now. So where did you stop and start with how far your suggestions go here on some of that hardware level?
It's a great question. So we very rarely see clients deploying on like H100s or B100s. The kinds of clients that we work with are like enterprise and corporates, which might have access to either the previous generations of GPUs or maybe slightly cheaper GPUs. So we tend to do most of our benchmarking on those kinds of GPUs. And we support NVIDIA and AMD, and we're rolling out support for Intel as well. We have seen good results on AMD. We think they're a really interesting option. And then for Intel, we're kind of waiting for the software support to catch up there. And we also know that like Inferentia are doing interesting things and the TPUs are doing interesting things as well. So there's definitely more out there than the B100s and H100s that you see. And for most enterprises, you really, really don't need them, and that you're probably fine with previous generations of NVIDIA hardware. My recommendation would be to stick with NVIDIA, mainly because the software stack is a bit more evolved. But I would build your infrastructure and applications such that you can move to AMD or you can move to other providers in a couple of years, because my guess is that gap is going to close pretty quickly. So you don't want to tie yourself to like an NVIDIA native everything. Out of interest, what are you guys using?
we're using OpenAI off of Azure, so
Okay.
we're using NVIDIA,
Yep.
but I'm looking to build something out locally because we'll balance loads between cloud and on-prem for development or even just spilling over extra load. So
Yeah.
keeping mind open to everything, but great talk. Thank you.
Yeah. We have something funny, which is one of our selling points is that we are hardware agnostic, so we can deploy on not just NVIDIA but others as well. And the conversation always goes something like, "Can I deploy on AMD?" And we're like, "Yes." "Do you use AMD?" "No, but I might want to." So it's a good thing to keep your options open there.
Anyone doing self-hosting inside a company at the moment? Self-hosting the model?
Nice. One,
Few, not many.
couple. It's very cool.
Yeah, thanks for the presentation. Could you elaborate on some of the batching techniques?
Yeah. So if I go back to batching, so let's assume we're not going to do no batching, and we're going to do some kind of batching. So if I'm doing dynamic batching, what's happening is this is batching on a request level. So let's say my batch size is 16. I'm going to wait for 16 requests to come in, and then I'm going to process them all. If I am in a period of very, very low traffic, I'll also have some kind of time as well. So maybe either 16 or a couple seconds, and then I'll process that batch. What that means is I get kind of this spiky workload where I'm waiting for long requests to finish and stuff like that. What we can do instead is this continuous batching. So what this allows you to do is it allows you to interrupt very, very long responses with other responses as well. So this means that we can do essentially like token level processing rather than like request level. So I might have a situation where I have a very long response, and I can interrupt that response every so often to process shorter responses as well. And it means that my GPU is always at very, very high utilization because I'm constantly feeding it new things to do. So we end up with continuous batching, which is much better GPU utilization.
It's token level.
Yeah.
From there. Okay, cool. Any other questions?
Apologies. I consider myself a bit of a novice in the space, but I just, maybe it's just me, but how does interrupting and giving it a different task improves GPU utilization? Why is not just continue with the current task gives you the peak utilization at all times?
It's a good, so essentially it's because otherwise you have to wait for that whole request to finish and the GPU is able to process things in parallel. So it doesn't actually affect the quality of the output at all. It just means that for each pass I can just have it predict different tokens from different requests. So it's constantly being fed with new things rather than waiting for the longest response to finish, and it's only working on that one response while we're waiting for a new batch.
So you're suggesting I can put multiple requests in at the same time?
Exactly.
In a single request to the GPU?
Exactly.
I see.
So what you end up with is your latency on average is a little bit higher, but my throughput is much better. Mm-hmm. So if I batch these requests together and process them together, I end up getting much better throughput than if I was just to process them one by one.
Okay. And apologies for this silly question, but when I do give it a long-running request, what is GPU doing if it's not being utilized 100%? What is taking that long?
Sorry, what do you mean?
Why is the request taking that long while GPU is not being utilized? What is going on in that setup?
When the GPU is not being utilized?
Yeah, but you're saying I'm putting in a long-running request, so it is running.
Yeah.
But what is running if the GPU is not being utilized at the same time to maximum capacity?
Yeah, so if it's essentially doing each request one by one, so I have to wait until the next one. But we can, afterwards, I have a fairly good article, I think Base 10 wrote, that I'll share with you, which also was very, very good in this, and I can also pull up some examples out of my phone on that.
Thank you.
Thanks.
Cool, thank you. Any other ones before we call it? All right, if not, let's give another hand for Meryem. Thank you.